In my last video, my last live stream, I was reading out of my book, When Time Ends, and I read the preface or preface, depending on where you're coming from. And again, the purpose of this channel is to help my sister get to sleep. So, not exactly touching on gripping subjects, but somebody recently said that reading this book, they were doing some proofreading, put them to sleep. So maybe a video of me reading it would help people get to sleep. And that's where we find ourselves right now. Section 1, Prerequisites. This is the introduction to this section. Um, let's see. The world is ending, or at least that's what today's entertainment would have you believe. Orson Welles captured the minds of many with a radio presentation entitled War of the Worlds, broadcast on October 30th, 1938. Some truly feared that the world was coming to an end. Just a few years later, on July 16th, 1945, the first atomic bomb was detonated, one of the first demonstrations of mankind's ability to make good on the threat of worldwide destruction. Now, some 75 years later, the various systems used by man have become even more precarious and provide good reasons for taking precautions to prepare for an uncertain future. This publication is one of those precautions. Whether it is a massive solar flare that wipes out technology, putting mankind back into the era of the horse and buggy, or a major geological event that shifts the rhythm of the Earth's movement, mankind could lose track of time altogether or even lose the ability to measure time accurately. What is time? Movement is time. Movement is observed at every level, from the motion of subatomic particles to galaxies that traverse the universe. A clock doesn't measure the passage of time, it only harmonizes movement. A quartz movement and a clock vibrates. This type of clock harmonizes this high frequency movement with divisions of time used for Earth's low frequency movement of hours, minutes, and days. If you lose time, you have to set the clock again. In a deep, dark cave, there is no movement of the sun, stars, or the moon that's really discernible to human beings, and no sense of time. This publication was prompted by the desire to observe changes to Earth's shape after a cataclysm. Using a long measuring tape around the equator and poles to measure the Earth is laughably impractical. The best way to directly measure the Earth would be by satellite. That type of resource would be likely unavailable after a major cataclysm. The best indirect way to perform this is by taking advantage of the relationship between mass and movement. Movement is to observe, time something, and then observe it again. So, in this case, we need to observe the Earth's position in some form or fashion, discern the passage of time, and then observe the position, in this case, of the Earth again. In this case, the Earth is being observed using astronomy. Time generally is the movement of the Earth or a clock. After a cataclysm, the Earth's movement is in question, so it can no longer be used as the source of time, and many clocks would be lost or inoperable. A secondary clock is found in the world of astronomy in the movement of Jupiter's moons. Subtitle: Shifts in Time. The history of calendars is messy. Religious institutions have been largely responsible for tracking the large scale passage of time, namely with the use of calendars and associated systems. One list of calendar systems includes 86 variants used by mankind over the millennia. Advances in technology have heightened mankind's awareness of the accuracy of these calendar systems, and this has improved access to accurate and precise timekeeping methods. Precision date and timekeeping is a rather modern concern. The Julian calendar, named after Julius Caesar, was entered into use in the year 45 of the Common Era. Unfortunately, it did not accurately reflect the tropical year, that is, the amount of time it actually takes the Earth to orbit the Sun relative to the equinoxes. By the 16th century, the error was a full 10 days, which had to be corrected when the Gregorian calendar was first implemented in the year 1582. It took over 300 years for the rest of the world to discontinue the use of the Julian calendar. Just a few years later, in 1608, Dutch lens maker Hans Lippershey filed a patent for the first telescope. News of this device reached Galileo Galilei, an Italian scientist who improved on Lippershey's design. Galileo turned his telescope towards the night sky and, on or about January 7th, 1610, he discovered Jupiter's moons. This moment was the beginning of a major shift in scientific and social reforms. Motivated by the close relationship between timekeeping and astronomy, in 1656, Dutch astronomer, I'm going to butcher his name, Christian Huygens, completed a prototype for the first pendulum clock. This design improved clock accuracy and reduced error from approximately 15 minutes per day down to 15 seconds per day. Note that the International Institute of Standards, or SI, established that the standard unit of time is the second. This is the foundation of timekeeping that is established in this publication by performing astronomic chronodetermination and repeating the observation events whose interval of time is known, namely the movement of Jupiter's moons. Astronomic chronodetermination is the determination of the date and time when using the position of astronomic bodies. This procedure is the focus of the sections 3 through 6 of this book. Modern timekeeping. Timekeeping and astronomy are also closely tied to navigation. In 1707, the loss of four British galleons due to navigational problems prompted Anne, the Queen of England, to establish the Longitude Act of 1714. This compelled John Harrison to invent the marine chronometer in 1730, the first accurate clock for navigation. Since then, timekeeping has increased in both accuracy and precision. Pendulum clocks were used for high precision timekeeping until the invention of the quartz crystal regulator in 1927, which was supplanted by the atomic clock in 1955. Presently, the United States Naval Observatory handles its responsibility for maintaining accurate time by employing dozens of atomic clocks housed in some 20 thermally regulated vaults. These atomic clocks are synchronized and feed a time signal to various distribution methods, such as network time protocol servers, or NTP servers, that connect to computers over the internet, and the time based Global Positioning System satellite network. These satellites feed ground based mobile communication towers and deliver excellent timekeeping to end users around the world through various personal electronic devices, ranging from cellular phones to in vehicle navigation systems. Many devices are vulnerable to loss of time if isolated from these networks. Although the U.S. Navy largely discontinued training celestial navigation to officers around 2006, it was realized that the risk of a failure in the GPS system was too high. Only 5 years later, training in celestial navigation using handheld equipment started again. Here's a nice little image, a sketch of, let's see, these atomic clocks, satellite system, connects to cars, computers, cellular phones, cellular networks of different types, internet time servers. Okay. The concern about the delicate nature of these systems is not limited to military organizations. For example, in 1996, the Long Now Foundation was established, in part, to build a clock that will last 10,000 years. Housed inside a limestone mountain in West Texas, the clock is some 500 feet tall and consists of assemblies that weigh up to 5 tons. The design takes into consideration the effects of climate change. Being solar powered, it will continue operating even if there is a volcanic eruption and the sun is blocked for an extended period of time. It can continue to operate with just a single sunny day once every 10 years. Danny Hillis is a founding father of the Long Now. In a January 2014 seminar about long term thinking, Mr. Hillis discussed how melting ice caps would significantly impact the Earth's rotation and the need to synchronize this large clock with the Earth's motion. There remains the possibility that a number of different catastrophic events would shift the distribution of the Earth's mass sufficiently to change its orbit or rotation. When discussing this topic with the public, many have difficulty accepting the idea that the Earth's motion could ever change significantly. In fact, there's evidence that such events have already happened in the distant past and even during the relatively recent history of mankind. Subheading Deceleration. One of the oldest pieces of evidence of deceleration is highlighted in a March 14th, 2020 article in Popular Mechanics by Daisy Hernandez. This article explains that fossils of the Turrietis sanchezi, a type of prehistoric clam, provide evidence that the Earth's movement was different 70 million years ago, stating, quote, the bivalve fossil explains the reason for the shorter amount of days in the year. Total amount has decreased from 372 to 365 days, something we can attribute to the moon and subsequently the oceans. The resulting friction from ocean tides has been ever so slightly slowing the Earth's rotation down. Modern example comes from the shifts in the Earth's mass due to man-made projects. A June 18th, 2010 article from the Energy Watch by Cutler Cleveland states, the Three Gorges Dam in Hubei Province, China, is the world's largest hydroelectric power station by total capacity. The reservoir will contain about 39.3 cubic kilometers of water. That water will weigh more than 39 trillion kilograms, or 42 rather, billion tons. A shift in a mass of that size would affect the rotation of the Earth due to a phenomena known as the moment of inertia, which is the inertia of a rigid body with respect to its rotation. The moment of inertia of an object around a given axis describes how difficult it is to change its angular motion about that axis. The longer the distance of a mass to its axis of rotation, the slower it will spin. You may not know it, but you see examples of this every day. For example, a figure skater attempting to spin faster will draw her arms tight to her body and thereby reduce her moment of inertia. Similarly, a diver attempting to somersault faster will bring his body into a tucked position. Detaining water behind a dam increases the distance of the mass from the Earth's axis of rotation, which slows the Earth's movement. While this illustrates the Earth slowing down, the Earth also speeds up due to the same laws. The earthquake off the coast of Japan on March 11th, 2011, is suspected of increasing the Earth's rotational velocity. A March 14th, 2011 article by Alan Buis from the Jet Propulsion Laboratory in Pasadena, California, discusses how earthquakes impact the Earth. A complex model applied by research scientist Richard Gross, also of NASA's Jet Propulsion Laboratory, indicates, quote, the Japanese earthquake should have caused the Earth to rotate a bit faster, shortening the length of the day by about 1.8 microseconds. While last year's magnitude 8.8 earthquake in Chile, Gross estimated that the Chile quake should have shortened the length of the day by about 1.26 microseconds, and calculated the 2004 magnitude 9.1 Sumatran earthquake revealed it should have shortened the length of day by 6.8 microseconds. End quote. Possibilities. Subtitle. Imagine an Armageddon level event. Questions would arise, such as, did the Earth's mass shift enough to perceivably change its movement, the position of the poles, the planet's orbital rate? An event of that level could produce pressing questions regarding the ice caps, the change of ocean levels, the formation of mountains, and even the tectonic plates and their volcanoes. Astronomy and math are at the heart of providing answers to those questions. Subheading Scenarios. The following are four basic scenarios that will help the reader decide how to proceed according to their own particular circumstances. 1. Cataclysm has just happened. An array of telescopes and clocks are available. It could be that the ocean's water has receded from the shores locally. The reader needs to know if the Earth has changed shape globally or if it was a local event. Is the ocean's water coming back? There could be an urgent need for more information about changes to the Earth's geography and climate. For example, if winter is looming and a mass migration or building project is being considered. If the reader is familiar with astronomic equipment and has a reliable clock, a quick assessment of the planet can be covered with a clock with a check of the sidereal day mentioned in chapter 3 of this book. To better understand the severity and length of a winter, check the location of the northern celestial pole and the Earth's axial tilt or obliquity of the ecliptic using chapter 14. These 2 points can be reviewed quickly in less than a day or two. A cataclysm, second bullet point here. A cataclysm happened some time ago. Only the components for making a telescope and a pendulum clock are available. Under this scenario, there is not an urgent need to make decisions. The priority would be to gather the elements for making a telescope and clock. Optics and a clock would be salvaged from pre cataclysm manufactured goods. Third point. The cataclysm may have happened some time ago. No telescope or timepiece is available. Without access to optics or a clock, there will still be a number of things that can be accomplished by making a large but simple sextant. The northern celestial pole can be found. The observer's latitude and even sidereal time can be observed. The approximate distance to Jupiter can be calculated. Recapturing the Gregorian date and universal time by observing Jupiter's moons and determining the length of a second requires an optical aid of some sort. A cataclysm, fourth point, fourth scenario. A cataclysm has not yet happened. Telescopes and clocks are readily available. This would be the case for readers under the circumstances at the time of writing. That means right now. Therefore, from this point forward, the objective is to present the information in a logical and straightforward manner that maximizes retention with the possibility of being used in the future. First chapter will discuss practical methods for proceeding to determine the current circumstances of the planet. A cheat sheet, you might call it, is presented in this little book, A Measure of Time, which is the compact version of this with some formulas and ephemeris data star charts and such being provided throughout. This was released through Amazon about a year ago. And I might have a link to it below. I have to check into that here in a minute. But we'll get to that. Let's see. Okay. Back to the reading. The first chapter will discuss practical methods for proceeding to determine the current circumstances of the planet. Chapter 1, Perspective of Time.